Welcome, everyone. You are joining us for Advances in LED Illumination for Fluorescence Imaging. This webinar is presented by Excelitas Technologies Corporation and hosted by us at Photonics Media. Today, you're going to hear from Dr. Kavita Aswani. She is a senior biomedical application scientist at Excelitas Technologies. She received her doctorate from the University of Iowa and has 7 years of scientific research experience and over 20 years of applications experience in the microscopy and fluorescence industry. In this session, Dr. Aswani is going to talk about how LED illumination for fluorescence microscopy systems has progressed. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access a recording of this webinar online after the event, and you will receive links to that in your email inbox. So with nothing further from me, I'd like to welcome Dr. Kavita Aswani. Welcome.
Thank you. Should I start? Because I don't see too many attendees.
Yes, you can start now.
Okay. Can you see my screen?
Yep, everything looks good.
Perfect. So welcome, everybody. I'm Kavita Aswani. I've been with Excelitas for 12 years now. And I will be talking to you today about advances in LED illumination for fluorescence imaging. And that could be fluorescence imaging through a microscope or an endoscopy or any other fluorescence application. So just to give you a bit of a background about who we are, Excelitas was our company, which is outside Toronto, was founded in '84 as EFOS. We have been Exfo, we have been Lumen Dynamics, and most recently we are now called Excelitas Technologies. We initially started out as UV curing systems, and then we introduced fluorescence illumination and X-Cite. So the company has changed names a few times, but the brand has always been X-Cite and is known for fluorescence illumination. So what is X-Cite? X-Cite was the first HBO alternative, and HBO is the big black or gray box that would sit on the back of microscopes. We were the first alternative to HBO with pre-aligned lamps that, pretty much go into the box like you would in your homes. It was very easy. You don't need to align them. And of course, initially we started out with lamps, but now we have progressed to LEDs, and we sell a lot more LED systems than lamps. Our systems are direct coupled, which means the unit actually just sits on the microscope, or there are liquid light guide systems too. So if you can see here, this is a liquid light guide option, and this one here is a direct coupled option. And we are a key supplier to the major microscope companies. So why would you want to upgrade from lamp to LED? Well, LEDs, lamps have flicker. It's very common in most AC lamps. LEDs have no flicker. The lamp needs to warm up. It needs to cool down. LEDs are simple on and off. You just press a button and it goes on. Press a button, it goes off. There's a slower intensity loss over time, whereas with lamps, you lose about 30% intensity in the first 400 hours. Even though the lamps do last quite a bit longer now than they used to, you still have the intensity loss, which makes you unable to compare, old images with new ones. LEDs are more stable. They have more repeatable output power, whereas in lamp, the power drops again, as I said. LEDs have longer lifetime. Lamps are usually about 3,000, maybe 4,000 hours, and you need to stock bulbs, whereas with LEDs, it can go from 10,000 to 25,000 hours, depending on the system. LEDs are less phototoxic to cells because it's simple on and off, and you don't have to leave them on all the time. Whereas with lamps, there is more phototoxicity and bleaching. LEDs have less power consumption than lamps, actual electric power. In LEDs, there's no mercury. With lamps, there's a larger environmental footprint because you have to dispose of the mercury or the xenon bulbs. With LEDs, there's no consumables. With lamps, you have, obviously, you have to keep bulbs in stock. And with LEDs, you can actually select specific wavelengths. With a lamp, you have to rely on a filter wheel in order to select the wavelength of interest. So just to show you here the intensity over time, in red here we have LEDs intensity over how many ever months of use here, whereas with the lamp, you start out, you have to replace it within 10 months, you put in a new one, it degrades eventually, and basically this is showing you how LEDs make more sense than lamps really in terms of lifetime. Another way to put this is if you look at HBO, which is the big black box that sits on the back of the microscope, versus the X-Cite lamp systems. This is our own X-Cite lamps versus one of our LED systems. You can see the total cost of ownership between the replacement lamps, the light guides, the bulb disposal. You can see the savings that you get. Basically, there's nothing to do with nothing spent. And if you look at energy consumption, you can see the comparison between HBO lamp and our LED systems. So just to give you an idea of how LEDs are making headway in the market because of these very reasons, and of course the fact that we do want to go greener. So a little bit of history. Why are we still using mercury lamp systems? So if you look at a mercury lamp spectrum, this is what it is. And a lot of the fluorophores we use today, your DAPIs, your FITSIs, your generic fluorophores, were developed using this spectrum, right? And LEDs suffer, and this is why I'm saying because it's in the past. We have now fixed this issue. But between the 500 and 600 region, LEDs do not have very high power. Lamps did, and they and a lot of the fluorophores in this region were developed around these peaks that lamps possess, but LEDs do not. And LEDs were not bright enough for certain applications that involve very high power because the fluorescence signal is very low. So this green gap between 500 and 600 is because of the lack of semiconductor materials that emit in that area. And this is an issue for fluorophores that have green, yellow excitation and red emission. And that's why lamps and lasers were traditionally used for this particular area, because there was nothing available in the LED world. So what we did to resolve this issue is we have something we call the laser LED hybrid drive. And that is our patented technology where you have a laser phosphor. So a laser is used to excite a phosphor that produces high power between the 500 and 600 nanometers. And that is what we are able to use to fill in this green gap. So just to show you the progress in filling the green gap, when we initially started out with our first LED system, in the green, this green curve shows you our power between the 500 and 600, and you see it's pretty low. Then we progressed to another product. This is around 2015 time, and you can see that the power is still fairly low, but it was, a little bit of a progression. Then I'm sorry, the blue curve here is lamp. So you can see the peak of the lamp between the 500 and 600. This was our first LED system. In dark blue was our second LED system. And now we are around the red curve. So we have done very well in filling this green gap, and we are able to provide our customers with equivalent power as they used to have with lamps. So now, why are we still using Xenon? So Xenon curve right here, this is 175 watt Xenon. It has a pretty uniform spectrum, as you can see, throughout the visible wavelengths. And it is used in ratiometric imaging. And what that means is that you're taking a image at, let's say, the 340, and you're taking another image at 380, and you need to make sure that the power that is reaching your sample is equivalent between those two wavelengths. So then you can do a ratio between one and the other for calcium imaging. Also, xenon lamps go far out into the near IR. And what that allows you is deeper imaging. You're able to image a lot deeper with the higher wavelengths. So what's the issue with xenon? Well, the systems are very, very large and heavy and expensive. It is still a bulb system, so bulbs need to be replaced and disposed of. And switching between the colors relies on the speed of your filter wheel. With LED, it's less cumbersome, it's less expensive. LEDs last for thousands of hours, tens of thousands of hours. You can instantly switch between colors. So if you're using the 340 and the 380, you can instantly switch between the two without having to wait for the moving of a filter wheel. And because it's LED, the wavelength intensity can be individually controlled. So where I'm heading with this is, excuse me, calcium fluoride ratiometric imaging, which has always been an issue for LEDs because you don't have, or they didn't have, 340 and 380. So calcium is important in several cellular processes, your muscle contraction, neuronal signaling, and changes in the calcium provide insight into dynamic processes in living cells. So Fura2 helps you detect changes in calcium or calcium fluxes. So what you do is you start with a Fura loaded cell, excited with 340, excited at 380. Then when you add your calcium or there's some sort of calcium influx, you measure again at 340 and 380 at the same intensity of the 340 and the 380. Then you take the ratio of these images, 340 to 380, you record it over time, and you can see the changes in calcium that are occurring. And Fura excitation goes up from 380 to 340 in the presence of calcium. So if there is calcium, you'll have a larger Fura signal. So, excuse me. So just to describe this new product that we have, it goes from 340 all the way to 800 nanometers. So it goes from Fura2 to IR800, and I'll explain to you the importance of IR800 in a bit. This product has 9 high-power switchable channels for fluorescence imaging, and we do have the laser LED hybrid drive in this unit, so you can isolate your spectral bands within the green gap, the 500 to 600 range. It has pre-installed cleanup filters for your most common fluorophores. You can control it with our handheld speed dial, USB, or TTL, and analog control options. So you can turn on and off each channel individually, and you can control the intensity of each channel separately using analog voltage. And this unit comes in 4 configurations. So if we look here in the blue, you have one flavor. So it covers your DAPI, CFP, FITSI, covers your green gap, covers Psi5, Psi7. The green version is the same as the blue version, except instead of having a 365, you have a 385. So some people like to use 385 for DAPI, others like 365, depending on your setup. The third version is your X-Cite Fura, Novum Fura, and you can see you have a 340, you have your 380, and you have the rest of your fluorophores. And then we have an IR version, which extends all the way out to 800 to excite your near IR fluorophores, such as ICG or IR 800, which I will talk about in a bit. So just to give you an idea here of the progress that technology has made, in the orange here, we have one of our units that was launched in 2015. In the green, you have a product that was launched in 2018, and you can see the powers, of course, in the new Novum, which is in the blue, have significantly increased over the years. And if you compare it to our own lamps, so in the yellow here, you can see one of our lamps, which was like the gold standard in the industry. In the green, you can see one of our broadband light sources that was launched in 2018. And the blue is the X-Cite Novum, which is what we're discussing here, that goes from Fura to IR800. And you can see that we're actually beating our own gold standard lamps. So just to show you how this unit works in comparison to traditional Xenon, which is what people used for Fura imaging. Excuse me. So here's some HeLa cells that were loaded with Fura for about 30 minutes. The time-lapse imaging was performed, and triggering between the 340 and the 385 was done with continuous acquisition to capture the baseline fluorescence in each channel and the ratio metric imaging change due to the agonist. Once you add calcium to these cells, you can see how there's a difference in the actual image. More green means there's more calcium present. And in this case, ionomycin was added to induce a calcium flux. In another example, these are dorsal root ganglion sensory neurons, and you can see that from blue it turns into a little bit of a yellow, green, or even a red once you add capsaicin, which is another chemical that elicits calcium responses. So here is another demonstration of this previous slide, where you have your baseline, and once you load the capsaicin, you can see a response here and a higher response when you load a higher amount. And your potassium chloride is just shows that they're healthy neurons. So this is another example of how your low resting baseline calcium level in blue, and this is with rat cortical pyramidal neurons, and a response to 100 micrograms of glutamate triggers a rapid calcium flux, which you can see here in green. And this is a similar calcium response to glutamate with the cortical neurons, which is concentration dependent. And you can see that you get a similar response with the control, which is potassium chloride. So these are just examples of how the system is actually working to provide the same results as those which were provided by Xenon in the past. And this is just another example. You have your phase image. You have your calcium ratio at baseline, Fura ratio at baseline, and when you add NMDA to elicit a calcium response. So newer applications, a lot of customers were asking us for, do you have something in the 700 and the 800 region, a 700, 800 nanometer region? And we really didn't have a solution, and it was primarily lasers and xenon that was used for the more IR applications. So ICG is indocyanine green, which is widely used in surgery to label plasma. It's very popular in ophthalmic angiography as well. So why do you want to use something in the IR or in the near IR? It's because it has a higher signal, lower background, and you can penetrate a lot deeper into tissue in vitro or in vivo. And ICG is actually FDA approved. So if you look here, this is an actual example of how ICG is injected into the blood. It stays within the vasculature, so it shows you which vessels are well perfused and which aren't. So this example is this is a laparoscopic cholecystectomy, and you can see that this is the bright field image. But so if you then turn on your IR light, you can actually see the fluorescence. So you can see how this particular organ is infused with blood vessels. So this and this helps surgeons make sure that when they're performing a certain procedure, that obviously they don't cut through blood vessels, because that would not be good. But also to make sure that if you have a tumor and you want to resect the entire tumor, there's another fluorophore that will enable you to see the tumor and make sure you're cutting out all the tumor while you're not cutting any blood vessels. And here's just another example. This is a image of a bowel, just with normal white light. You turn on the fluorescence, and you can see the actual perfusion of this of blood in this particular tissue. So just to kind of end the presentation, I guess I talked a lot faster than I hoped to, but the LEDs can be used in analytical environments. So if you're talking about fluorescence microscopy or microfluidics, fluorescence plate, slide scanners, microscopy, digital mirror devices, or endoscopy or surgical visualization, LEDs have moved to replace xenon and mercury in a lot of these different settings. And I guess I spoke very quickly. Any questions?
Thank you.
Sorry.
Evan, thank you very much. We do have time for a few questions. Everyone, if you have not already, please go ahead and type your questions and comments into the webinar chat. Okay, so my first question for you is, are there any other fluorescent markers used in surgery?
Yes, so I touched on this briefly. There is a tumor marker called PP9 ALA, and that excites around the 400 nanometers, and that's a tumor marker, which is used to make sure that you resect the entire tumor. But so you can turn on the UV, look at the tumor marker, make sure you cut out all the tumor, and then you can turn on the IR to make sure that you're not cutting through any blood vessels.
Thank you. All right, this next question says, I didn't see a 340 nanometer peak in your chart, only 380. How are you able to excite Fura at 340 nanometers?
That's a good question. So the Fura peak is quite low in the Novum system, but because it's LED based, you can then tune the 340 and the 380 to be at the exact same power as you would do with Xenon. So it's simply a matter of turning down the 380 until it matches with the 340.
Perfect, thank you. All right, this next question is, can the user control the laser light in the hybrid drive?
So no, the laser light lives inside the unit. Nothing actually comes out of the unit. The laser excites the phosphor, and what comes out of the unit is the emission. So there's no laser light leaving the unit.
Okay. And this next one is, how do you actually switch between colors?
So you can switch with the handheld controller or with USB or TTL, and it's just a matter of pressing a button.
Perfect. All right, this next question is, what has the feedback been for Fura labs who have switched from HBO?
So Fura would be Xenon lamps. and not so much HBO because they require the power to be exactly the same. And all the stuff I showed you today was all from real labs, and they are switching from Xenon to LEDs.
Perfect, thank you. All right, this next question is, does your company provide custom-based LED arrays, for example, LEDs on a ring?
Yes, that is possible. Maybe not with our particular site, but yeah, for sure.
Perfect, thank you. The next question is, what is the advantage over super continuum sources which can provide a higher brightness and a broader spectrum?
Price. Super continuum is very, very expensive. A lot of people can't afford it.
Thank you. All right, this next one is, what is the switching speed of the Novum 340/380?
Good question. I can't remember, to be honest, but it's within microseconds.
All right, thank you. So I think that's all the questions we have for today. What I want to say is there is some very nice comments in here saying how wonderful this presentation was, and I just agree. I would just like to say that everyone, if we have not gotten to your question already, please look out for a reply from us later. If you think of another question, you can let us know by emailing webinar@photonics.com. That's WEBINAR@photonics.com. And just a final note, this whole session was recorded. It will be available on Photonics Media website shortly, and you will receive links to that recording by email. It does look like we are receiving a few more questions. Sorry about that. Do you mind if we do a few more, Kavita?
No, go ahead.
All right, thank you. Let me just see which other ones we have. So this one's long, but it says, my question is about these light sources, about how these light sources are integrated with the rest of the system. For example, synchronizing the excitation with camera exposure. Also, are the light sources compatible with software such as Micromanager, LabVIEW, and MATLabs?
Good question. So a LabVIEW can control any of our light sources, Micromanager as well. A lot of the microscope companies have us integrated, and if they don't, because it's a new product, we can fake it to be one of our older systems. For example, one of our 6 LED wavelength systems. So we can cheat the system by telling it it's one of our older systems, so you can see at least 6 colors. How it's integrated with the camera, again, that would be with the third-party software. So you can synchronize the light source with the camera.
Perfect, thank you. I have another one that says, do you have a 800 nanometer only unit?
No, we don't. We don't do single wavelength systems. We do multiple.
Perfect. So I'm just scrolling through, see what other questions we have. This one says, is it possible to use MFish app?
I'm sorry?
It says, is it possible to use MFish app?
I am not aware of the MFish app.
Okay,
If
we
you
can get back to you.
Yeah, if you can email me, is it Murat? We can discuss further because I am not aware of this. Oh, multicolor. Yes, yes, absolutely. You can do fish with this system. And because fish has such low signal, with this unit and the power that it has, you can definitely be used.
All right, perfect. I think that is all the questions we have for today. So again, if you guys think of any other questions, please email us. And just a final note, this whole session was recorded. You'll receive that link. And I'd like to thank Dr. Kavita Aswani from Excelitas Technologies one last time. Thank you. And thank all of you for participating in today's event. It was presented by Excelitas Technologies Corporation and hosted by us at Photonics Media. Thank you.
Thank you. Bye.